Hi, folks. Welcome to CF Summit 2019 in Europe. Hope you're having a good day. Welcome to my talk on volume services. My name is Paul Warren from Dell EMC, and I've been an engineer on the volume services team since its inception. Standard disclaimer. I'd like to take you on a journey from that beginning all the way through to where we are today, so that you can understand better the offering that we provide, how it works, why it works the way it does, and some of the decisions that got us to where we are today. So for those that aren't familiar, what are volume services? Volume services in CloudFoundry are the ability to bind one or more shared volumes into your application container. I say shared, and shake your hand. I say shared for a reason, because you can only attach NAS shared volumes into your application containers. So we don't do block. The reason for that is that CloudFoundry at the heart has the Diego-based scheduler, and that is a scheduler that's optimized for 12-factor applications. And to cut a long story short, the services that you bind to your applications running on this scheduler have to be able to handle more than one thing connecting to it at once. And that's why we don't do block with CloudFoundry on Diego. We'll get into a little bit of block at the end. So in the beginning, there was just CloudFoundry. There were no volume services. Well, of course, there were volume services. They existed. You just couldn't connect to them from CloudFoundry. But we wanted you to be able to connect to them from CloudFoundry. And we wanted to expose those services just as any other service. So we created an NFS broker. We gave that thing a database so that we could persist service instances and service bindings across restarts of the broker, which you have to be able to do for when you're deploying updates to your CloudFoundry deployment. That then gets taken down and brought back up again. We also modified the Open Service Broker API to have a volume service construct so that service brokers could issue service bindings with volumes in them. Along the way, we had to touch some of the existing CloudFoundry components. We had to touch Cloud Controller, BBS, Auctioneer, and the rep, make them all a little bit familiar with what a volume service is. On the cell, we had to put a volume manager, and paired with the NFS broker, we had to put an NFS driver, the thing that's actually going to provision the mount for you. And we proved this architecture out with a Ceph-based broker and driver originally, but we didn't want to take that for a couple of reasons. We didn't want to take that into production. So it seemed to make sense to move in the direction of NFS, given that we have a Linux-based operating system at the heart, and also because that was the signal we were getting from you folks, right? We wanted something that was generally useful. So how does it actually work? Well, when the developer pushes his app, obviously it uploads the application bits to the blob store, and it creates a record of that new application in the Cloud Controller database. That then allows the developer to create a new NFS service and specify the share that he wants to bind into his application containers. What's actually happening here is we're not actually going and creating a share on the back end for a couple of reasons, right? The signal we were getting from the community initially was that they wanted to take their legacy applications and lift and shift them into CloudFoundry. Yeah, this was some application that had been running in a data center for years. It had been reading and writing files to some share for years as a particular user. But it was a pain to keep that thing security patched, and occasionally it fell over, and then the operator had to get out of bed and restart it. Lift and shift that thing onto CloudFoundry, right, and you kind of get all that for free. The other reason we don't provision shares is that it's not actually part of the NFS protocol itself. So NFS deals with the mount and reading and writing of files, but it doesn't actually manage the life cycle of the shares. And we as a team consider that we support the protocols. So you specify the share that you want to associate with. Cloud Controller talks to NFS, and basically NFS is just recording the fact that you're going to bind that share later on. Developer then binds his application to a service. So it's looking just like any other service. Cloud Controller talks to the NFS broker. The NFS broker issues a service binding with a volume mount in it. And you can see this is the section of the service binding specific to the volumes. It's targeting the NFS driver on the cell. And here's the share that we want to bind in. And really, we haven't placed anything yet, so that's just recording or associating the share with the application. So then the developer starts his app. Cloud Controller talks to BBS. BBS wants to know where to run this workload, so it's going to hold an auction. One of the cells, and I depict the cells here, right? There's 3 of them, but it could be any number. One of the cells is going to win that auction, cell 1 in this case. BBS talks to the rep on that cell and says, hey, see these application bits over here? Can you run them in a container for me? The rep looks at that specification and says, well, actually, there's a service binding there, and it's got a volume in it. So it asks the vol manager to provision that volume. The vol manager obviously sees the NFS driver, knows that's the driver it wants to provision the share, and it forwards that onto the NFS driver. And the NFS driver does a mount of that remote share. So at this point, you have the remote share mounted over the top of a local directory on the cell. The NFS driver then returns this local mount point back to the rep. The rep says to Garden, take those application bits, run them in a container, please. And by the way, could you bind this directory into it? And so it does. And at this point in time, you have an application that's free to read and write files to that remote share. And that was the very first version of what we got working. But there was a problem. For every single build pack that you run or you push to CloudFoundry, the user inside the container always has a UID of 2000. And that maps to a UID on the cell outside the container of 1000. And because NFS is a POSIX-based security model, user 1000 is going to be the guy that's fiddling with the files on your remote share. Now, bear in mind, this is, in the early days as well, was all about lifting and shifting existing applications. 99.99% chance that's not the user that has been fiddling with the files on the share, right? You need it to be someone else. Most likely, user 1000 doesn't even have access to that share. So we had to think about this, and we thought, well, that's okay. When you do binding, we'll allow you to specify the UID of the user that you do want touching the files. Cloud Controller talks to the NFS broker. NFS broker responds with the service binding with the volume in it, specifies the UID that you want to use, and then we fast forward to placement. The NFS driver does the kernel mount as it did before, but we then do a second mount over the top of that mount with a special fuse module of our own devising called MapFS. And the sole purpose of that thing is to map the current user, UID 1000 in this case, to the intended user with the UID of 999 in this case. And then the NFS driver returns this to the rep, and the rep binds that second mount into the container. Now when the application reads and writes files, it's doing so through that second mount, which is mapping the user from 1000 to 999, in this case, on the way out, and mapping it back again on the way in. So that's what we called MVP, minimal viable product. But of course, it was a bit lousy because it wasn't very secure. Right? The user could specify any UID, and we would try and bind it for him. Moreover, CF doesn't have any rate limiting on its API, so if you knew there was a share out there. So back to the drawing board. We thought Kerberos is built into the NFS protocol. This is OK. We'll allow the user to specify the username and password on bind service. And then if we fast forward to app placement, we'll then try and initialize a Kerberos security context. And then on the mount, we'll specify that we wanted to use Kerberos security. But this was a bust. It didn't work for us. We could initialize that first security context, but we couldn't initialize multiple security contexts. It was way too bound to the host machine. And bearing in mind that this was happening on the cell, we could have any number of applications placed on that cell, all requiring different security contexts. So back to the drawing board again. We thought, this is okay. LDAP's probably the most common IDP out there. Maybe there's something we can do there. So we kept the ability to specify the username and password on the bind service. And then when it issues a mount, we include the username and password. And then when you start your application, if we fast forward to app placement, before we do any mounts, the NFS driver contacts an LDAP server with those credentials and verifies them. If they check out, we exchange those credentials for that user's UID. And then we do the exact same double mounting process that we saw earlier, and we bind mount that second mount into the application container. And at this point, we had a secure solution. And by the way, when we run with LDAP enabled, we turn off the UID capability. Okay, so this was reasonably secure. The customers then started to say to us, yeah, that's good, but we want to use application manifests and volume services. And of course, we just given them a solution where you have to specify the username and password in the bind service, can't specify -c parameters in your application manifest. So this meant that we had to capture the username and password during the create service, not the bind service, which meant that we had to remember the username and password in between the create service and bind service. And because it was a password, that meant that we had to remember it securely. So we added CredHub as an option to run the NFS broker on top of. And that meant that we could remember the username and password securely. And that also meant that when you started your app, you could specify your application manifest with your volume service in it. And then during that start process, your volume is bound automatically. We can include the username and password information in there because we've remembered it securely in CredHub. And we fast forward all the way through the same process, right? And the application's placed on the cell. So that gave us a little bit more flexibility. I think at this point we were fairly feature complete, and we kind of graduated from experimental with a lot of you folks, and you actually started using us for real. And you said, hey, yeah, I like the performance of your stuff, really sucks. And this wasn't too much of a surprise to us, because when we do that kernel mount, we run with caching off. We turn all caching off. And that was deliberate, because when you push an app, you can scale it on the platform to multiple instances. And so we didn't want to affect data integrity. So we run with caching off to force every client back to the server for every request. But of course, that comes with a performance penalty. Right? So we talked to these people that were trying to do this, and they said, well, actually, you know what? The use case we've got is some other process drops a massive file on an NFS share, and then all our CF client apps are doing is really reading those and doing some batch processing on that file. And we said, all right, fair enough. That's okay then. If you specify read-only, then we'll include that in the service binding. And if we fast forward to app placement, when we do the mount, we won't do the caching. We won't turn the caching off, sorry. So we'll run with default caching. And then you'll get a bit of a performance improvement there. And they said, great, thanks very much. By the way, it still sucks. And we said, okay. And they said, well, you know what? These aren't lift and shift use cases for us. This is net new. These shares are net new. So we actually don't care who's reading the file. We're quite happy to open up access to UID 1000. So we said, okay, fair enough. Oh, what happened there? Oh, I remember. My bad. Pardon me. So we said, fine, if you don't specify a username and password or a UID and GID, depending on how you're running, then we'll get rid of the MapFS here, leaving you with just a kernel mount. And then you should be back to the performance that you get with just a regular kernel mount. And they said, great, that's fantastic, thank you very much. So that gave us some level of performance in somewhat of an opinionated way. Then we had other customers who had unreliability issues. We never quite got to the reason whether it was nodes in their NFS cluster that were unreliable or if it was just the network that was unreliable. But something in there was unreliable. And this customer sometimes had mounts that took a long time. Well, what happens there is if it takes longer than 10 seconds to place the application or the workload, then BBS is going to get bored and it's going to cancel that and go and try and place that workload elsewhere, doing all of the clever Diego stuff that it does. But it does send us a cancellation when it's going to cancel, and in our code we've done a pretty good job of routing that cancellation signal all the way through to the NFS driver, and we did what we thought was smart. We cancelled the mount command. But this customer was saying to us, yeah, but we still have like mounts on the cell and we have no associated workload. It's kind of like an orphan mount. We were like, that doesn't sound quite right. So we dug into it a little bit. And what we discovered was when you do a kernel mount, the kernel mount turns right back around and forks a subprocess to do the specific type of mount. In this case, it was forking a mount.nfs subprocess. So I guess you probably guessed what happened. We got that cancellation signal when the BBS got bored of waiting and went to place the app elsewhere. We'd done a really nice job of cancelling the parent mount process, but leaving the subprocess still running. Now, if your unreliability went away, and that mount then finished successfully at some point in time, you're left with your orphan mount on the cell. So that wasn't ideal. Fairly easy fix, though, to modify the code to cancel the process group rather than the process. Right. Same deal with unmount, right? That could theoretically take a long time. We get the cancellation signal, we kill the unmount. And then you're probably left with an orphan mount again. The operating system came to our rescue there. There's a -L flag on the unmount, which stands for lazy unmount. What this does is it disassociates the mount from the file system and returns success immediately, allowing us to return success almost immediately to the rep. Whilst in the background, the operating system will take care of unmounting that, and shepherding that process through the completion. So a nice, easy solution for us in the end. So at this point, that gave us a nice, fairly feature-complete offering. It was reasonably secure. You got reasonable performance in an opinionated way, and we were fairly reliable in the face of flakiness. So it worked, but it's quite complicated. The NFS driver has to know about the LDAP server. Usually the person who manages the CF deployment isn't the person who manages the LDAP deployment. So this usually means tickets to get the connection details, to go open up security groups for the LDAP server or the LDAP deployment, allowing traffic from the set of cells, which are the IPs, the set of cell IPs. Moreover, when the developer does need a new share, that probably means more tickets too, because the developer probably isn't the person managing the LDAP deployment either. And this one's a little bit tricky because as part of the NFS protocol, part of the security protocol for NFS, you have to specify the set of IPs that have got access to this share. Developer doesn't normally know what the cell IPs are, so that's more communication, more tickets to try and get that hooked up. We've got MapFS on the cell, so there's more mounts there than people expect. There's more mounts, there's more processes, more things to go wrong. And the final kicker is that even if things are working great, the traffic for NFS goes across the wire in plain text. It's totally unencrypted. So whilst we were working on this, we'd also been working on SMB, and it works the same way. Right? There's an SMB broker, there's an SMB driver, and you usually have obviously both on the cell at the same time. And this allows the developer to create an instance of an SMB service rather than an NFS service. It works the same way. You specify your share. It is just an association. We're not provisioning it. It's just in UNC format instead. And then when you bind your service, you specify your username and password, just like you do with NFS. That issues similar sort of binding, but it's targeting the SMB driver, not the NFS driver. And then when you start your app, we do a CIFS-based mount, not an NFS-based mount. And then, oops. And then we take that mount point, and we hand it back to the rep, and we ask the rep to bind that into the container. So you'll notice there's no MapFS mount on top of this. And this is because authentication and authorization is built into MapFS by default. so we don't need the complexity that we have with the NFS solution. Moreover, if you have anything resembling a fairly recent NAS on your back end and it supports SMB v3, then the client on the cells will negotiate up to SMB v3, and your traffic across the wire will be encrypted for you by default as well. So I think you agree, overall, simpler solution. So a word on locking. We support, or we consider that we support the NFS protocols only, those being the protocols only, those being NFS and SMB. We don't, as a team, we do not certify against any backends, any NAS's backends, including Isilon. We provision the mounts only onto the cell and into the container, and then we take them away again afterwards. Right? There is a tiny bit of code in the data plane for NFS in some situations, that being MapFS, but that does not have any locking code in it. Right? It is devoid of locking code. It does one thing and one thing only, which is to map that user on the way out and map it on the way back in. So feel free to go ahead and use locking. But if you're going to use locking, you probably want to take a look at a few things. You probably want to understand the locking calls that your application is going to make to the operating system. And what I mean by that is, if you have a Java application and your developers are writing some sort of locking code in Java, you need to understand what the JVM is going to do down at the operating system level. And then once you understand that, you probably want to go and understand the locking calls that the operating system is making over the wire for the version of the mount that you're doing, because it's different, especially in NFS, from different versions. And then you probably want to, it's not on the board there, but you probably want to start to have a think about what it means if you're using version 4 of NFS and SMB, then when a client opens a file, it will take out a lease on that file. That's a performance enhancement that allows the client side to read and write to that file without going back to the server, because it knows the server will come and break that lock later on if it has another client that wants to write to that file, giving the first client the opportunity to write the changes back. That's all great and all, unless you have unreliability and the server can't break that lock. In those situations, I think you can run into some data integrity issues. So feel free to use locking, but proceed with caution. And if you do try, we would love to hear some stories from you. Right? We would love to talk to you about that. So takeaways. Use SMB when you can. It's simpler and it's more secure. Our assumption is that most NASs nowadays can export a share as both either NFS and SMB. So again, let us know if that's not the case. Use NFS by all means if you can't use SMB. But hopefully at this point, it's fairly resilient to failure. And if performance is a key, pay special attention to the mount options you're using. If you can get away with read-only, go for it. If you don't need UID mapping, don't use it, and then you're going to get a regular old kernel mount and the performance and caching associated with that. So a quick look forward. I'd like to, you'll notice that I haven't mentioned Windows at all during this talk, and that is because my PM, Julian, over here, is about to do a talk with Daniela in Everest, just across the way right after this, and they're going to talk about volume services from Windows applications. And then tomorrow, Julian's going to do another talk on pushing Mongo. So this was about a recent POC we did, where running with CF on top of Kubernetes, we were able to push an image of the Mongo database, scale it up to 3 instances, each one getting their own block device, and then run that as a cluster, and write for one node and read from the others, which for us from Dell EMC was quite exciting because we've been trying to find a way to do block for about 3 years, and I think we found a route forward. So what does the immediate future look for us? So that's our service offerings today, but what does the immediate future look like? Well, the CloudFoundry on Diego code line, we're considering it going into maintenance. We're going to do bug fixes and CVEs on that. But we're going to turn our attention to CloudFoundry on Kubernetes. And in the first instance, we're going to focus on, our charter says we're going to focus on feature parity with CloudFoundry on Diego, and we're going to go after SMB first because we think that's a much better fit for this cloud-native world. Again, please let us know if you think those priorities should be done differently. Once we get through that, the plan is open. We don't have anything in our backlog or our charter past that. We think we would like to go after block, but we would love to hear from you guys. Do you have use cases where you need to be developing application-based workloads that require block devices? Another area we could go to is brokers. It's always bugged me a little bit that it's an association only. I'd like to have brokers that provision, which I think would reduce the inertia of using volume services. But we'd love to hear what you guys think. That's just what I think. What do you guys would like us to do? And lastly, locking. As you probably can tell from the locking slide, locking with NFS and SMB is a little bit fraught with danger. It can work if you're careful about what you're doing. If you are going down that road, or you have the opinion that volume services should just make locking work, we would also love to hear from you. And we'd love to discuss further with you what working actually means. The plan is open. We would love to hear from you guys about where you think we should go next. And at that point, I think I'll open up for questions. How did I do? All right, well, 1 minute over, but yeah.
Quick question. So in this case, all the scenario what you mentioned was one instance.
Yep.
So how will it, like when we scale to multiple instances?
Yeah.
It's the same.
Yeah.
Multiple of them are writing to a common record.
Yep.
So how do we do locking them?
Right. So we don't have any code in volume services to manage locking. So if your application has that requirement, then I think it's best to be very cautious as you proceed and really understand the applications that what your application is going to be doing, and take it from there. We're not going to do anything other than provide access to the locking features that are supported by the operating system and the protocol in question that you're using.
Is there an option where each instance can spin up its own NFS mount?
That is how it. All accessing the same share, you mean, or?
Yeah, so it's the same share.
That is actually. Yeah, that is actually how it works today. So each workload, each app instance will get its own mount. In days gone by, we were trying, and if the app instance got placed on the same cell, in days gone by, we tried to be clever and kind of have one mount and reference count, but we moved away from that for several reasons. So each app instance will get its own mount.
Its own mount?
Yeah.
It doesn't really fundamentally solve the locking problem.
No.
Because the locking problem is no different from what you would have with two instances of your app running on different VMs, right? You still have concurrent access to parts of a file. And if you're going to use locks, you have to reason about it in the same way you would with a legacy app on VMs.
Anyone for any other questions? Okay, I'll be hanging around outside for a few minutes and then I'll probably go into Julian's talk, but you can come and find me if there's something you want to ask.